Hi everyone, in this video we're going to look at triple integrals, which is one step further from double integrals, which means we're working with functions of one more variable, that is functions of three variable. So these functions are going to be hard to visualize because their actual drawing of what they look like would exist in 4 dimension, but we will use certain tools in order to kind of make sense of them, because these are functions that get 3 inputs and produce 1 output. So you have an x, y, z as input, and you get output as some single variable. For example, temperature in your room can be given by, say, a formula x plus y plus z, which, I mean, that's not what the temperature would be. But this is an example of a function which is 3-dimensional. It takes x, y, z, and it outputs temperature. So what you can think of it is, here's your room, zooming it to be square. So at every point in your room, the temperature is going to be different. And so this is one way to visualize it, is if I take a sort of gradation. Let's suppose that it's your room it's cooler on the corners over here, and then as you get in, it's warmer, and it's really warm at the center. So this is an approximate drawing of what a four-dimensional or a 3-dimension and a function of 3 variables would look like. But we have to use color in order to visualize that 4th dimension, because we cannot see it. But the point is that we can visualize this simply by looking around us. So for example, if you look around you, in whatever room you're placed in is probably made up of vertical and horizontal planes and lines, because that's how we build our houses and buildings. So which means if you look to some corner in your room, you can imagine that the one going up is the axis, and y-axis and x and y-axis are on the floor. And when we say a function of 3 variable, you take any point in your room, assign a value to that point, and basically you have a function of 3 variable. And that's what we're doing. So we're integrating over 3 space. So we're integrating over x, y, and z. And what are we integrating is some density function which provides values to each point in space. And that's essentially what's happening. And just as in double integral, there's going to be the simplest version, which is just a bunch of boxes. So we have Fubini's theorem for triple integral, which says that if f is continuous on a box defined by the room that you're in, or a comma b cross c comma d cross r comma s, then the integral can simply be done as a iterative integral, just like a double integral. So we can iterate it thrice and find the value. For example, if this is a triple integral, all I'll do is boom, 3 integrals x, y, z squared. I go dx, dy, dz. I read off the limits. X is 0 to 1, y is -1 to 2, and z is 0 to 3. There'll be again 2 ways of doing it. One is you can simply go x dx, 0 to 1, do -1 to 2 y dy, and 0 to 3 z squared dz, and just multiply the result, right? So this would be 1/2. This would be another 1/2, but 4 minus 1, which is 3, and this would be a 1/3, and a 3 cubed, so 27. So these cancel out, so you get 27 over 4. Or you could go sequentially, that is, work with to the dx part first, right? So that will give you 1/2, and you have 1/2 y squared z squared, -1 to 2 dy dz, 0 to 3. Now you work with the y, so you do the dy. That will give you a 1/2, another 1/2, and a 4 minus 1, 3, and you still have a d squared dz, 0 to 3, and you get a 1/4, a 3, a 1 cube, and a 27, which is again 27 over 4. So it gives you the same result as expected. And that's because this is the simplest form, which is a box, right? So here it's like it's an actual 3-dimensional box where we are evaluating the integral over, instead of it being a region. So that's the Fubini's theorem. Then the next since you're familiar with this from double integral, we have a general region. We might not always have a box. Because now we have three variables, x, y, and z, we have more than one alternative here. In double integral, it was just dx dy. Right here, if you imagine, you can actually have 6 different ways of doing it. You have a dx dy dz, a dx dz dy, a dy dx dz, a dy dz dx, a d, so on and so forth. So which means there will be 6 different ways of doing this. So let's start with the first one, which is called a type 1 solid region. So a type 1 solid region, what is the definition of a type 1 solid region, or what are we calling a type 1 solid region, is if the limits or the shape is such that the z is the part that varies. So it goes from z u1xy to u2xy. In this case, we will project it down to the xy plane and get this region. So here what we are going to do is we are going to do the dz part first, right? Going from u1xy to u2xy. So we're going to integrate with respect to z and replace all the z things with u1, u2, which is basically x and y. So then we are good for the second part. And then the second part, we're going to do a dA, which is a double integral. Now, for double integral, we know that there's more than one way of doing it, right? So when you have a double integral, if the region D comes out to be such that it's the y that varies, right? Then you have u1xy, u2xy, that's going to remain the same. So this is dz first, right? And if it can be expressed as y equals g1x and g2x, then you would do y next, because then you would go from g1x to g2x, so you are left with only x terms. And then in the end, you would do x, where x varies from wherever, which is a to b in this case. And the second option is, so again, keep in mind that this remains the same because we've already established that this is a type 1 region. And when we have type 1 region, we do dz first, right? Now it's the second part here. If it's easier to express x in terms of y, and y goes from c to d, then I will go dx first and make it go from h1y to h2y, and I will go dy last, which goes from c to d. So this already gives me, two different ways of doing it, right? And these are dz dy dx and dz dx dy. So as you can imagine, there's going to be 4 more, right? Because you can have dx dy dz dx dz dy, and those are basically going to be if I project it on this plane and if I project it on that plane. So we'll look at that in a bit. First, let's look at an example of how to use this particular. So we're trying to find this triple integral over the region E, where E is the solid in the first octant bounded by z equals 12xy and the planes y equals x, x equals 1. So hopefully from Calc 3 you remember and are sort of familiar with how to work with three-dimensional space. We don't use quadrant anymore, we use octant because there are 8 possible things. And again, look around you, some room that you're in, that's one octant, right? That's the room across. On your floor, there's going to be 4 rooms, the neighboring your room. Those are the 4 top octants. And then below is going to be your negative values, and there's going to be 4 rooms. So all of those form those 8 octants. And the room that you're sitting in is 1 octant. And for visualization, we can always assume that to be the top number 1 octant where everything is positive, which is also called the first octant, meaning x, y, z are all positive. And what is now, let's understand what's been asked, right? Z dv, z. So what's happening is you're in the box, right? In the first octant bounded by z equals 12xy and the planes y equals x, x equals 1. So let's try to visualize what that is. We get z, and I draw it slightly differently here, xy at an angle here. Now, z equals 12x plus y is is a hyperbolic structure, so it does something like that. But y equals x is a straight line, and x equals 1 is this vertical line here. So what you have here is sort of a skateboard-ish ramp shape, but getting straighter on the other end, on one end. And z is the mass distribution. So imagine in your room there's a shape like this, and at each point is not contributing 1 unit to mass, but z unit to mass. That's basically the interpretation here. Okay, so if you look at this is z equals, this top part is z equals 12xy, and this bottom part is z equals 0. So it's bounded between z equals 0 and z equals 12xy. So this is we can convert this into type 1. What it means to convert this into type 1 is we're going to project it to xy axis. So when I project this to xy axis, if you look at the shadow of this object, the shadow of this object is going to be this triangle. So we'll end up with this, which we call the region D. So it's for uniformity, whenever it's 2-dimensional, we call it D. Whenever it's 3-dimensional, we will use E. And what is this? This is x equals 1 here, and this is y equals x. So we will go from this. Okay, so first I know that z, I'm going to go dz, because z goes from 0 to 12xy. Then I'm in the 2-dimensional region now. So here, it's easier to write, well, both of them are kind of easy, but x goes from 0 to, or y goes from 0 to x. So I will do dy goes from 0 to x, and then x goes from 0 to 1. So first I get a 1/2 12xy squared. I have dy 0 to x and a dx 0 to 1. So they cancel out, 144, and this becomes 72 x squared y squared dy dx 0 to x 0 to 1. 72, first do the dy, that becomes 1/3 y cubed, which becomes x cubed, which becomes x squared x cubed dx. So 24, then 1/6 x to the 6 0 to 1. So 4 times 1, which is 4. So this triple integral comes out to be 4, which can be understood as a volume. We will see later. Volume when the distribution of mass or distribution is when the density function is given by z. Okay, so that's an application, or that's an example. Next, as I mentioned, there are 4 more ways in which the integral can be evaluated, and they would be called type 2 and type 3 regions. So if the solid region is such that it can be written, expressed easier with x as y of yz and u2 of yz, then we are going to project this into the yz plane. So what's going to happen in this case? In this case, we will have first a dx, which goes from u1 yz to u2 yz, and then we will have a dA, which will depend on the region D. So there will be 2 possibilities here again. The first possibility is we take this, let's copy this is going to remain the same. It's going to remain the same. Okay, so the first possibility is I go dy, let me change the color. Now it becomes a 2-dimensional problem. So I go dy, which goes from I don't know, some function of like FGH. So okay, let's use G. So G1Z to G2Z, and then the last one will be with respect to Z, which goes from R to S or something like that. Or it could go DZ, in which case it's like H1Y, h2y, and then a dy, which goes from C to D. The other way is if you start off with a shape that looks like this, which will be type 3. So then you have u1xz, u2xz. In this case, the first integral will be dy, and then you will have the dA over the region D, which will again break down into two possible things. So essentially, the 6 possible ways you can have is f, x, y, so dx, dy, dz, right? So if we copy this, so you have 2, 3, 6. So what are the 6? So you have dx, dy, dz, dx, dz, dy. You have dy, dx, dz, dy, dz, dx, dz, dx, dy, dz, dy, dx. So it depends on which one is easier, which also means that, well, okay, I'm going to stop this video here. Next video we'll look at an example of how doing it in one particular manner will be easier than doing the other. In fact, it may not be possible to do it in one of these 6. And what that also means is how in double integral we had 2 options, right? So if we couldn't solve with one, we were changed to the other. Here we have 6, which means if it doesn't work in one, if we end up with something we cannot find the integral of, we just try another, and it will probably work in there. So I'll end this video here, and we will continue with some more examples and see why having 6 options is helpful and how going from one to the other can help us solve some of the problems. Okay, that's it for this video. Thank you.